So moving on to the laws and rules, we'll have to, in this section, then look at how you can apply the different laws like the commutative law, associative law, distributive law of Boolean algebra, as well as how the 12 rules can be applied. So Boolean algebra is based on the 3 laws plus 12 rules. We have the 3 laws as commutative law, which talks about the order of the variables. We have another law, associative law, which talks about the grouping of the variables. And then we have distributive law, which talks about the use of brackets. For all intents and purposes, you realize that these laws are already intuitive to a lot of you because you already know algebra. So the similar laws apply in the normal algebra that you've learned from high school. So on top of the laws, then there are the 12 rules that most of which also would be intuitive. So looking at the commutative law, what the commutative law simply says is the order of the variable does not matter in the end or functions. What it simply means is that if you have A plus B or A or B, then the result will be the same as you have when you have B or A, which is also intuitive. That the order doesn't matter. It doesn't matter if you put A on top or B on top, then the result will always be the same for that function. Similarly, for the end function, when you have A and B, will behave exactly the same or will give the same result as B and A. The associative law, which talks about grouping, means that the grouping also it's relevant. It doesn't matter whether you start with B or C and then you take the result of that, you put it through an OR gate with A. So you have A or a group of B or C. The result will be exactly the same as when you have grouped A or B first and then you have C later. So these two results will be equivalent. Similarly, the grouping of B and C and A will give the same result as the grouping of A and B and later C. So the result will be the same. So these are pretty much intuitive as I've stated. Then the distributive law says the bracket can be broken. So what that means is if you have B or C, the result and A, then you can multiply out the A into the bracket so that we have A, this is equivalent to A and B or A and C. So like normal algebra, you can factor out that common factor. So this means in terms of the circuit, that the output of this circuit, then it's equivalent to that particular circuit. Remember, the whole idea of this Boolean algebra is to help us to be able to design digital systems. So the expressions can always be made into the equivalent logic circuits. Now looking at the 12 rules, the first 9 for me are very much intuitive. So the first one simply talks about the fact that when you have A or 0, that is A plus 0, so anything or 0 will always be A. What it means is that if you have 1 or 0, the result is 1. If you have 0 or 0, the result is 0. So this variable A, it doesn't matter. As long as you have this variable A, will always be shown here. If you add it to the 0, so that's what the first one means. In a similar fashion, then when you have any variable and you put it through an OR gate with a 1, the result will always be 1, because an OR gate, when one of the outputs is high, the result will always be high. Then from the behavior of the AND gate, in this case, you can also see that if you have one of the inputs as a 1 in an AND gate, it doesn't matter what the other variable is, your result will always be 0. Because in order for an AND gate to have a 1, all of the inputs have to be 1. And then the next rule, A and 1. So when you have through the AND gate A and 1, your result will be A. What this simply means is remember the variable A can either be 1 or it can be 0. So in the first case, you will have 1 and 1. Your result will be 1. In the second case, you can have 0 and 1. Then the result becomes 0. So what this shows is whatever input A is will be copied to the result. So this explains this rule number 4. So rule number 5 says if you have A or A, then your output is A. What this simply means is, if say for example your A is 0, then you will have 0 or 0. Then your output is going to be 0, which is also A. If you have your A as 1, you will have 1 or 1, which means your output is going to be a 1, which is also the value of A. So it makes sense in that sense. The other interesting one is rule number 6. When you have a variable plus its complement, then the result will be 1. The reason for this is, remember, this is an OR gate, so which means if you have an A or its complement, they will always have an opposite value. So which means the inputs here, one of them is always going to be 1. If A is 0, then the complement is high. If A is high, then the complement is 0, which is why then you have your value always being 1. Then the next rule, number 7, if you have A and A, the output is A. Number 8, if you have A and its complement, the output is 0. Similarly, this one is intuitive in the sense that you see, in this case, for rule 8, either A or A complement will have its value as 0. So with an AND gate, whenever one of the inputs is 0, then you always have a 0. Another one to note is rule number 9, which says if you have A and you take a complement, if you have the complement of A and you take a complement of that, then you come back to A, which means if A is 0, then if A complement is 0, then A complement is going to be the opposite of A complement, which is 1. Yeah. From there on, then I will move on to explain the next 3 rules, which are a bit more, which take a bit more time to try and understand. So in terms of rules which are a bit more complicated, for lack of a better word, to prove them, there are generally 2 ways which we'll talk about. The first way of proving that indeed this part is equal to the other part of the equation is to use Boolean algebra itself, the other rules. And the second way is to use a Venn diagram. So let me start first by using Boolean algebra itself. So beginning from A or A and B, you will see that this is equal to A and 1 plus A and B. Remember, this comes from rule number 4. This comes from rule number 4. Now, which therefore means that if we use the distributive law, we can have A, 1, or B. This is the distributive law, because then we can distribute the common factor around the bracket. And then this is equal to A and 1, because according to rule number 2, the whole of this result becomes 1. And now, similarly, according to rule number 4 again, A and 1 will be equal to A. Therefore, what we have just proven is that the right hand side A is equal to the left hand side A plus A and B. The second way of looking at it is looking at each of these variables to represent a set. So you'll see then, if say we imagine we have a Venn diagram where the yellow region represents A and the gray region represents B, then it means the intersection here will represent A and B. Now, what A or A and B means is we will be taking the union of A and B. So because we are saying we are looking for all the values that are in A or in A and B. So if you look at that region, the whole of that region, then that region becomes equivalent to simply A. So we can try and prove rule number 11 by starting on the right hand side with A or B. So you can see that A or B is simply equal to A or B and 1. This is according to rule number 4. And then from there on, we can see that we can have A or B and A complement. This is according to rule number 6. Rule number 6. Remember, when you have a complement or its a variable or its complement, then you will always have a 1. So you can write that according to rule number 6. Then we can use our distributive law to have A or AB or A bar B. You can use the distributive law, and then we can also then say this is the same as say A and 1 or A B or A bar B. This also going back to according to rule number 4. Then we can make a bracket here selectively A or B or A bar B, right? Then according to rule number 2, we can have this as A or 1 plus A bar or B. So for that, yeah. So according to rule number 2, this 1 or B simply absorbs into an equivalent 1. Then, according to rule 4, then it means, therefore, we can simply have A, because A and 1 is A plus A complement and B, which then proves that this left-hand side is equivalent to this right-hand side. So using the Venn diagram, another way of viewing this is the result here. On the left-hand side, you have A, the union of A, and with the intersection of A complement. A complement is like everything that's outside A, where it intersects everything that's inside B. So that is what you have in this case. So if you look at the diagram here, we are saying we have the union of A, which is the yellow part, all of that plus everything that's inside B, which would be this purple part, including the intersection. Everything that's inside B, where it intersects everything that's outside A. So this is the purple part. So that gives you the left-hand side. Now that should be equivalent to, when you look at this is simply equivalent to when you simply have the two shapes and you have A or B. So it's simply equivalent to the stuff that you have in A plus the stuff that you might have in B. So this then becomes equivalent. So you can use the Venn diagram to prove it that. So looking at rule number 12, we can see that this effectively represents the intersection of two regions. So this is the intersection of two regions. The first region is A union B, and then the second region is A or C. So it's the intersection of those two regions. Now the way it works is, what happens in this case is the first region, A or B, it's highlighted here in yellow. And then the second region separately, A or C, it's highlighted also here in yellow. Now the result here should be the intersection of the two regions, where this region intersects this region. So if you look at the result here, you will see that these regions have in common, both of them have A, that's the first thing, and both of them have that region where B and C meet, which is why then you have the result of the two intersections as A or the intersection of B and C, which is the right hand side of the equation then. As already explained, the next best way of proving rule 2 is to use Boolean algebra. So this time around, beginning from the left hand side, we can use the distributive law to break the brackets, and then this gives us A multiplied by A plus AC plus AB plus BC. So if you distribute those two brackets, the next thing is to use rule number 7 to show that A and A is simply equivalent to A. And then we use rule 4 plus the distributive law to show that we can actually factor out the A. In this case, rule 4, we know that A is simply equal to A and 1. So we can factor out those common factors of A. And then we use rule 2 plus the distributive law, because then we are left with this being equivalent to simply 1. Then if you remember by rule 4 that A and 1 is simply equal to A, then we have A or BC, which gives us the left-hand side of the equation. Another way of looking at rule number 12, which is the left-hand side here, which is represented by this equation, it simply means that is equal to this other side, is represented by that equation, is to use the truth table. So you can always use the truth table to prove the equality of two sides. So remember, we have 3 input variables, and because of that, we have 8 possible input combinations. Remember, because this is Boolean algebra, the variables can either be 0 or 1. Now we can create, in this case, the result on the left hand side by first looking at the result A and B, and then looking at A or C, A or B, A or C, and looking at the end between them. So you can fill in the truth table in this case that so if you look at this one, A or C here is going to be 0 because it's all zeros in the input. And then A or B here is going to be 0 because both of A or B are 0. Here we're going to have 1 because B is 1. Here we're going to have 1 because B is 1, and so on and so forth. In the same way, we can fill in A or C to get these results, looking at A or C only. And then finally we take the intersection or the AND operation between this and that. So we AND them to give us that. Then we can fill in this row. Then we move on to look at the right hand side. There we can first create this combination B and C. So we look at B and C, and we'll see that B and C is going to be 1 here, where you have B and C both being high, and here only where you have B and C both being high, otherwise it's 0. And what we do is we look at B and C or A. So that combination, we bring it here, and we have so it gives us this result. But remember now, what we need to do is to compare if the left hand side is the same as the right hand side. So if you look at the left hand side, this then becomes the left hand side, this one, and then that becomes the right hand side. And if you look at the outputs here for all possible input combinations, this row, this column is equivalently equal to that column, and therefore this proves that A or B and A or C is equal to A or BC. So the other rules as well, you might use the truth table as well to prove them.